So there's something here that popped up. Okay, perfect. So the talk I'm giving today, thanks very much for everybody for joining in on this virtual meeting. So I'll be talking about the Proterozoic, the Paleoproterozoic, and how, after the Archean, you finally had tectonic regimes that resemble today's modern tectonics. And so the focus is going to be mainly on the Churchill province and the Trans-Hudson origin, which in my opinion and other people's opinion, it represents one very well preserved, complete Wilsonian cycle. So we're here, we have, in terms of, we'll start with nomenclature. Here's Laurentia and Baltica. And just one second here, I'll select a better, there you go. You get Laurentia here, Baltica on the other side. And what you have here in pink are all the Archean cratons, Superior, Wyoming, Slave, North Atlantic cratons. In orange, you have large swaths of Archean crust, which has been reactivated during the Proterozoic. There's the Hearn province, Ray province, Meta Incognita, core zone here, and so on. And so this entire mobile belt here is termed the Churchill province. And in Quebec and Labrador, it's named the Southeastern Churchill province here. Now, how does the Trans-Hudson fit in all that? The Trans-Hudson I've put here in between these hashed red lines is the area affected by the terminal collision of the Superior and North Atlantic craton with that Churchill collage at about 1.83, 1.79 billion years ago. So that's that area here. So that's the difference between Trans-Hudson composite origin and Churchill province. Yeah? And of course, within the Trans-Hudson origin, like many modern origins, it's a sequence of collisions that forms shorter-lived origin. There's a Fox origin, the Reindeer zone, the New Quebec origin here, Torngat origin there, and so on, with the Trans-Hudson origin representing the final collision. Now, if we start from the beginning, looking here after the Archean, there was a fracturing of Archean supercratons. And to illustrate that, here's the Superior Craton paper by Ernst and Bleecker here. And what it shows a whole bunch of radiating dike swarms of Paleoproterozoic age, with the stars here represent the possible plume heads, as was postulated in that paper. But I think here, in the Labrador Trough, we have remnant of what was called the biscotacing plume at 2170, where the radiating dike swarms from the Payne River dike and the biscotacing converge. And here's where they're converging. Here's a map of the Labrador Trough, or Southeastern Churchill province, core zone here, North Atlantic craton here, Superior Craton, Labrador Trough. There's mainly sediments here, mainly volcanics here in the middle, and then metamorphic rocks, hydrograde metamorphic rocks here. And this is what I call here the Labrador traps here, which is a large part of what they call the House zone. And what it has is it has classic traps structure with the stair-step structures here, which is flow upon flow upon flow, separated by thin sedimentary layers, forming this very nice topography. And this is what almost each and every one of these cliffs look like. Just beautiful columnar basalt, and you get on top, you see these perfect hexagons. And then you have composite flows with entablature, colonnade, and more entablature on top. And we've dated at least at two areas, at the bottom and the middle, and it's a very tight age at 2171, 2169. And so we interpret that as continental flood basalts. So these are not the classic Montagnais sills, but a much earlier suite of basalts, which is about 300 kilometers long by 80 wide. So it's quite voluminous. And so they have composite flows and sills, primitive tholeiitic compositions, geochemically similar to the North Atlantic igneous province, opening of the Atlantic, and Entong Java Oib, for example. And these are probably the oldest actually recognizable continental flood basalt provinces on Earth. Now, you had fragments of Archean continents breaking apart here, and formation of the of oceans, including the Manicouagan Ocean, and that is constrained by mafic dikes in the Wollaston Belt in Hearn here, and on the eastern margin of the Superior, the Cochon dikes and Courtenay volcanics, which many authors estimate as the opening of the Manicouagan Ocean at 2075. And Manicouagan Ocean opened, it's actually started to close at 1920. So if these numbers are good, it's 155 million years of opening of ocean, which is similar, but a bit shorter than today's Atlantic. And what you have when you open ocean, you have passive margins developing on the edge and intracontinental basins, and that produces a deposition of sediments, including marble, biff, phosphorites, which extract a lot of elements from the ocean: calcium, magnesium, iron, phosphorus, carbon. And you can actually see that, you can actually measure that as demonstrated by Melezic in '87. And also produces new deposit types, sediment-hosted uranium and copper, for example. So new things happening. Another thing that is preserved in the Canadian Shield in Laurentia is actually incipient ocean basin. And this is from a paper by Vorica et al., 2014, which looked at the stratigraphy of the Bravo Formation. So that would be northern Baffin Island in today's coordinates. And what you have huge effusion of incredibly well-preserved pillow basalts, as you see here, interlayered with black shales, sulfidic black shales. And the geochemistry is very similar to what you find in the Red Sea rifts, for example. Yeah. Another thing that happened in the Proterozoic is plate tectonics and thick origins, so plates colliding, forming origin. And what that does is that with production of origins, with deep basins, you also have an accentuated topography and more dynamic sedimentary transport systems. And an example of that, for example, is on Melville Peninsula here, where you have the Folster Lake group. And these are huge river deposits. They're arcoses, and see there's planar beds here on a cliff and 4 sets beds here, okay? And this is a person for scale here. So the 4 set beds are about like 8 to 10 meter thick, and more planar beds and so on. So it could be kind of a Gilbert type delta or something like that, but high energy flowing from west to east. And it was actually filling the Penryn piling groups. And what happened here, here's a photograph, an air photograph of the Longstaff Bluff Formation. It's actually a Google Earth photo showing the gray wacky turbidites. And right here for scale, you have a radar station, the Longstaff Bluff radar. So amazing, very nicely preserved folds in gray wacky. And we did the detrital zircon analysis from the Folster Lake group, and it has a peak at 1995, which is Telon orogeny. Another set of peaks at 2.3, 2.5, which is Arrowsmith orogeny, suggesting that indeed the sediments come from the west, transport toward the east, and forming these structures here in sediments. Now at 1.9 to 1.83, okay, so the ocean, Manicouagan Ocean, started to close actually. So it closed, it took about 90 million years to close, which is much faster than the opening phase, which is quite interesting. I don't know if that is comparable to more modern origins or not, where closure is faster than opening, or maybe it's just something peculiar about the Manicouagan Ocean. So what happens is that you close oceanic floor, you produce arcs. There's the Lynn Lake arc here, Flin Flon Glennie arc here, and Snow Lake arc down there. Here's a photo of the Flin Flon mine in the Flin Flon belt here. And according to Harold Gibson and all, This area is so endowed in VMS deposit. It's and the setting is very similar to what you find in modern oceanic back arcs. So the interpretation is that these deposits were formed in oceanic back arcs. And here's a series of cross sections from a paper, Corrigan 2012, in the lithoprobe perspective that shows a little bit. I won't go through details about that, but time sequences of closing of the Manicouagan Ocean. So essentially, you have a very modern-like settings with subduction arcs, back arcs, and so on, oceanic plateau. And one interesting thing here is that you have subduction of the snow, subduction here underneath the superior, forming the Snow Lake Arc, which is contaminated by continental crust, likely superior. And we propose that the Molson dikes were in place in a continental back arc setting. That is also proposed by Heeman et al. In a paper. On the other side here, you had accretion of the Lynn Lake belt to the Hearn Craton, forming molasse, 4 deep in molasse deposits and so on. And then an interesting thing here that we speculated about is that a subduction flip to produce the Waterman-Chippewan batholith. And so I'll come back to that a little bit later. So what you have in that time sequence 1.88, 1.87, you're starting to have accretion of microterrains like the Sugluk, Sask, and Corzone, and so on, and arcs to a already accreted core here of Slave Ray, and that was starting to build the supercontinent Nuna. So that was during the buildup of that supercontinent. Okay. Now the interesting thing here is that not everything is under convergence or compression. At the same time, around the superior craton, you get an emplacement of huge amount of mafic, ultramafic sills, the circumsuperior belt here, which is renowned for its very well endowed in nickel, magmatic nickel, and PGEs and so on, and copper. Here's just a picture showing the Chakotay group here in Cape Smith Belt. So the big question that has been, and it's still an open question, is that the consequence of having plume magmatism, with a plume sitting underneath superior and oozing out along the margin, or active tectonics, or maybe a combination of both. Just in terms of model, there's a mantle plume models, there's couple of authors and many others. The continental back arc model I just told you about by Corrigan 2007, Heeman 2009, here to explain the Thompson nickel belt. And in Labrador, again, it's a very tectonically active margin at that time, where you have a kind of a Gulf of California type strike slip opening here on the edge, producing the 1880 suite. That's from a paper by Skulski and in preparation by Van Rooyen et al. And Corrigan et al. So things can be in convergence at once. So if I go back here, things can be in convergence here and in extension here, depending on relative plate motions and so on. Now, the next big step that happened in evolution of the Churchill, if you want to put it that way, is formation of its organization of plates. So you had a collage of plates and microplates along that we call the Churchill upper plate here, and then organized subduction always northward or underneath that accreted margin. And that produced a continental magmatic arc at 1.86, 1.83. That goes from Saskatchewan, Manitoba, Hudson's Bay, all the way to Labrador. So you have the Waterman-Chippewan batholith, the Severn Arc, the older nice suite of the Nars Sagework Arc, the Cumberland batholith, and the Pa batholith here. And here's just an interesting photograph from the Waterman batholith showing the Park Island Arcos, the molasse basin that is intruded by the Waterman batholith here, which is a hornblende titanite bearing Pluton with arc signature. There's been a couple of models published to explain this this area, and one of them is subduction flip, and there's also slab break-off and delamination. Here we have a model of subduction flip where first you had accretion of the Labrador arc to the Hearn margin with southern subduction, and then subduction flips and goes underneath that accreted margin to form the Waterman batholith, which stitches the arc to the Hearn craton. And that is here a seismic section that was published in 2003 by White et al. That shows that section here across Yarra. So you have the Lynn Lake belt here, accreted to the Hearn margin, and the Kisinu belt here. And what they have in a seismic profile here is a 10-kilometer jog in the Moho, which they interpret here as a slab breakoff. Okay, so it's entirely possible that you had that, and that would be a very old scar preserved in seismic data here. Whalen et al. Was invoking slab breakoff or delamination to explain the huge swath of very high temperature orthoparkson bearing plutons of the Cumberland batholith here, which necessitated, according to him, a large amount of basaltic underplating and so on. Okay. So now I'm getting to the final punch, which is the indentation tectonics, so produced by the terminal collision of Superior with the Churchill plate. So here in a series of cartoons, I have A, B, C, and D, which shows the progressive evolution of that collision. And the first one here, you see Superior Craton, you see the intra-oceanic terrains here. You have the Flaherty Formation, Watts Group, Parent, Spartan groups in northern Quebec, and in Labrador Trough, the Géricault-Hurst Doublet zones. And then you have the accreted microcontinents in the Churchill plate with the continental arc, southern arc, Nars Sagework Arc, the Pas batholith, for example. In an earlier paper by Saint-Onge, he documents the possibility of terrain accretion as early as 1.87. So that's the first interaction between the Superior and whatever lies like to the north. Now, in a recent paper by Hodgkiss et al. 2019, they've looked at the detailed stratigraphy here of the Belcher group, which is essentially in Belcher Island, and it has a lower passive margin sequence, okay? And then above the Flaherty volcanics here, they document reversal of sedimentation. Okay, so and they dated that there's a tuff here at 1845. So they interpret that as, first of all, passive margin sediments with material derived from the Superior Craton. And at 1854, they get a reversal and deposition of a foreland basin and molasse basin on top of the passive margin. So that necessitates encroaching of some terrain here and building of an orogenic welt and deposition of a foreland basin here starting at 1854. One thing we did a couple of years ago, we actually dated an archival sample from the Loaf Formation, which is part of the molasse sequence, sitting on top of the Greywackies here. And the zircons give a large peak at 1841, 1861, which is classic arc, continental arc plutons from the Churchill province. It also had a little bit at 22, and zircons at 25, 22, 25, 33, which is kind of a rare thing in the Churchill craton, Churchill province. And also, if you, so what happened here is that, okay, you have encroachment here, then with further collision, you get deeper exhumation of granulites here in the Sudluk block and so on, and then deposition of a foreland basin here. But we also have deposition of foreland on the eastern side here as well. And these are examples of conglomerate from the eastern side, the Grand Rozois Formation. and also the Menihek Formation in Labrador, which interestingly has these large carbonate concretion, which is similar to concretions you find in the Omoralic here, which is a classic. If you're a quaternary geologist, you're looking for these things. But anyway, the interesting thing here going back to this this spectrum here is okay, for the Menihek on the eastern side here, we also did detrital work, and it essentially replicates what you see in the low formation with a large peak at 1840, 1860, and the small peak at 2500 here. So the next slide, I'm going to talk about this 25, the source of these plutons. So if you go back here, here's the Ungava Peninsula here, Hudson's Bay here, the other side, Labrador Trough there. This is an air mag map, oblique air mag that shows the Cape Smith Belt here with the Povangatuck, Shakotat, Parent, Spartan Group, and Watts, and forming the Cape Smith Belt. You get the Kovic antiform here and there, which is superior. Here's a little section. It's superior coming back up in an anti-form here. And here you get the Sugluk block, which is a term that was introduced by Paul Hoffman when we first worked in the Cape Smith area, or interpreted these area. So these are a continental block, an old Archean block in which a whole bunch of Proterozoic plutons were in place. And they're separated from the Kovic antiform and so on by the Sugluk suture. Here's a photograph of that suture, very high grade granulite facies rocks with a lot of melt. Here with top to the south thrusting. And the Sugluk block, okay, it has the 1863, it has a whole bunch of the plutons, the continental arc plutons from the Nars Sagework Arc, 1863 to 1824, but it also has the 2.55 plutons, and a couple of occurrences here along the coast, plus 2.88, 2.78, which is mainly found in islands offshore here. So if you look at our plot again, okay, from the low formation on the Belchers here, it has the 1841, 1861, all these plutons, and also the 2522, 2533, in area. So that makes it a very plausible source for deposition. So you need this. So this is where the main exhumation took place. And it's no wonder these are, if I go back here, just the colors, green is amphibolite, green schist facies, orange is amphibolite facies, gray is retrograde granulite, and mauve here color is the granulite facies. So this is where the main exhumation took place. So that begs the question, did we have kind of a Himalayan type lower crustal flow occurring here with preferential exhumation of those rocks, of the Sugluk compared to those here? Nothing is similar, and it would necessitate that we have a detachment here somewhere. There's been no detachment map so far, so I think it's still open question to what kind of mechanism resulted. Is it just straight exhumation and so on? Or is it crustal flow? That's a question to be addressed by future geologists or people who are going to go there in the future. Okay. Now this slide I've entitled, "Can the real Nars Sagework Arc raise its hand?" And I think there's a little bit of not I wouldn't say confusion, but there's many ways to interpret these plutonic suites that occur all over the north part of the Ungava Peninsula, and all called the Nars Sagework Arc or Nars Sagework terrain. So I'm just going to give a brief linking of these terms with historical development here. I think that one of the first papers that talked about the Nars Sagework terrain was by Dunphy and Ludden, 1998, and they did some work on some of the the 18-something plutonic suites that occurred in the Cape Smith Belt and Sugluk block. So they had divided it into three suites. There was the Cape Smith suite at 1898. It's kind of an older suite, which is relegated to the Cape Smith Belt here. And then in the Suglug block, they had the older gneissic suite, which is more of these Archean, and the younger suite, and so on. But they called the whole thing the Nars Sagework terrain. So they were linking all these together. And then later on, with mapping in South Baffin, Saint-Onge et al. Introduced the term Nars Sagework Arc to connect these 1840, 1820 plutons with those occurring here, and so on. But that, if you put everything as Nars Sagework, then it necessitates, if you look at the pink color thrust here, that you connect all the dots all together into one large Nars Sagework terrain. But if you see here, that suture goes right across the structural grain and so on. So an alternative to that explanation is that instead of having one large super suite, you have different suites in place in different blocks. So they're time equivalent, but not spatially equivalent. So you would have the Cape Smith suite in place in the Para-Spartan group here, the gneissic suite, the older gneissic suite in the Suglug block, and the time equivalent Cumberland batholith on Baffin Island. And a little bit later, explained by this cartoon here, you start to get convergence and producing of anatectic melts. And that is, those anatectic melts are the Nars Sagework Arc, which are actually periluminous plutons with garnet and so on, some of them with garnet. So, so in the preferred nomenclature that we're choosing, we have the Suglug block here into which the real Nars Sagework Arc was in place. So that is a bit different usage of the term Nars Sagework Arc. So there's a continental arc pluton in place in an Archean block. And that correlates here with the George River block, which has a similar history with the batholith. Anyway, on to something very I find quite interesting here, looking at gravity map of Canada and how you can extract this kind of information in the gravity map. You see here, well, the continental crust is about 2.7 grams per centimeter cube. Lower continental crust with granolites are a bit denser, 2.8 to 3 gram per centimeter cube, which is within the range of oceanic crust. So here's a good example here of the gravity high. You get granulite facies rocks of the Minto block here, which are Archean age granolites. Here you have the gravity high of the Cape Smith belt, of the circum-superior mafic magmatic belt that you can see going all the way around here. Here's the Fox River belt and Thompson nickel belt. And in that gravity map, you also see the Suglug block coming out very well. These are all granulite facies, and here's the Suglug suture and so on. And that turns around here and connects with the George River block here of the core zone. Yeah, so that's quite interesting if you're correlating things regionally. Now, another interesting, I would say, style of deformation that happened during this collision of the Superior with the Churchill plate is formation of Aurochlines. And that is very nicely exemplified by the curvilinear nature here of the Hudson's Bay reentrant. Here's the Belcher Islands here. Here's a map of the Belcher Islands that shows these very nice doubly plunging folds, and the folds go wrap right around like that here. And in the 60s, there was a lot of hydrocarbon exploration in Hudson's Bay. So here's a seismic line that was shot in the 60s and interpreted by Rock Sandick. I don't see the year, it's 1987, I think, which shows classic fold truss belts of the Belcher Islands over a décollement. And here's the Superior Craton here. And to the west here, you get Superior Crust coming back here. And this is interpreted, RS is reactivated Superior, that goes all the way here and into this area here of the Cape Smith belt, and back here in the Labrador Trough here. And just noticing here a very interesting, like classic mushroom shape fold interference pattern here, type 1 or 2, I forget. And so on. So these are very classic type of deformation styles imaged in the Paleoproterozoic. Now, the features you see here in Hudson's Bay resemble very much what you see on the western side of India, in Pakistan and so on, with the Suleiman range and the Makran range here. And here's the main thrust region of the Himalayas. And there's a little promontory here and a reentrant. And you see the style of fold is very reminiscent of what you have here. And which begs the question of, what was the mechanism for invasion of these naps here in that form forming Aurochlines? Is it vertical axis rotation, question mark? That would be testable with paleomag data, or is it radial flow, which is a bit more of a homogeneous penetration in terms of deformation style than vertical axis rotation. But these are interesting queries, interesting regions to, or not regions, but mechanism to try to get our handle on a little bit better. Now, on the eastern side of the Ungava indenture, the deformation style was very much different. Here you had, instead of having a confined reentrant, you had open ocean board at that time. It was not the Grenville origin, this was open here. So we had room for these blocks to move out. And this is exactly what happened. Here's an aeromag map of the core zone here. Here's a superior craton on one side, North Atlantic craton on the other side. And what you have here, you have at least 3 crustal blocks, which are separated by very steep shear zones. And what you have northern displacement of the superior craton and North Atlantic craton on this side, and actually southern displacement of these blocks. So they're getting extruded out along these shear zone here. And the interesting thing is most of the shear zones here are right lateral, so dextral, which is compatible with movement of these blocks towards the south. Although some areas like the Abloviac shear zone here, I think there's a lot of documentation of sinistral shear, so that's produced by North Atlantic craton moving north. But there's also, as shown in this photograph, a lot of evidence of dextral shear. Here's a beautiful little garnet here. It's not that little, it's kind of a big garnet, but it has a stair-step geometry. And the stair steps is actually a symplectite made out of orthopyroxene and plagioclase. So garnet goes to plagioclase and OPX, which is synchronous with dextral slip here. That reaction is very high temperature decompression at about 900 degrees C and 8 kilobar, which is quite interesting. So it's something we're working on. Diane Van Rooyen is working on paper analyzing these rocks and looking at timing and so on. So that should be quite interesting. And okay, and another example here you have a detail here of the there's the Pas batholith and the George River block, Mistini Bay Road block, and here's the Lac Tudor, Lac Turcotte shear zone and the George River shear zone. So we're right here. So here's the Lac Turcotte shear zone and the George River shear zone here. This is a scale 10 kilometers. So these are zones of very, very high strain and about a bit more than 10 kilometer wide each, with both shear zone having this dextral shear. But they also have these little late sinistral shear bands in the map scale shear band, which shows complexities of movement. So despite the fact that you do have North Atlantic craton moving north, superior moving north, these blocks extruding south, there is a lot of jostling happening between these bits that will sometimes reverse sense of shear. Yeah? So it's kind of complex, but it makes a lot of sense. And in terms of setting, I think Paul Hoffman and others in the past have used an analogy of Indochina here. And in terms of extrusions of blocks towards the southwest to try to explain extrusion of these blocks here. So that makes a lot of sense and so on. Okay. Now, the other thing is that there are some shear zones here which are mappable right across the origin for about 2,000 kilometers or more, that are essentially strike-slip shear zones. And one of them here is the George River shear zone, which can be traced to South Baffin, where it's the Soper River shear zone. And it goes all the way to the other side of Fox Basin in Hudson's Bay, which is called the Lion Inlet Shear Zone here, which we looked at a couple of years ago. And next slide is going to be here. And that's the north end of that shear zone, which, and you see here what's happening, it's dextral displacement. And you have oblique or transpressional tectonics here, where this block here is part of the Ray Craton, but it's a granulite facies block, and it's juxtaposed on lower amphibolite rocks of the Ray province with Penryn group. So there's exhumation, it's oblique exhumation here, okay? And you can actually follow that shear zone. It's been dated by Ganderton, 2013, and Laflamme at about 1810, 1820, which is the same age of displacement around here. So that's there's a very large continuous strike-slip shear zone right across the origin here, as you see in the Himalayas as well. So so again, very similar type of accommodation of deformation that you see in Paleoproterozoic origins versus modern origins. Now, the next slide, I'm going to move here on the western side of the Superior Craton. I'm just going to talk about that briefly. And so here's the Superior Craton, Saskatchewan, Manitoba, Hearn province here, with a whole bunch of bed. And what you see here is quite spectacular. It's poorly exposed, actually. I don't even know it's exposed, but most of it is not exposed, but it's quite nice on Air Mag signature here. And it's the Owl River Shear Zone, which is a sinistral slip shear that connects with the edge of the Superior Craton. And okay, so what happens here is what you see is that here's the exposed edge of the Superior Craton, and the Superior Craton continues underneath here. And this is likely the leading edge of the Superior Craton at the Moho and how it influences deformation. So these rocks are riding on Superior and these rocks are not here. Okay? And if I go back here, so this Owl River shear zones connect with one of these outer shear zones here that would go all the way to Big Island on the north side of the reactivated Superior here. And speaking of the western side of the Trans-Hudson, we're in Saskatchewan here, Manitoba here, Superior Craton, Hearn Craton. And what you have here is a wide swath of very well preserved supercrustal rocks of Paleoproterozoic age, Flin Flon belt, and so on, that were not exhumed very deeply. Okay, so, and myself and others, I think we've speculated that the reason why they haven't been overtrussed or strongly exhumed is due to the presence of a Archean core in the origin, which is the Sask Craton. Sask Craton is only outcropping a couple of places, but from geophysical experiment, it's shown that it takes the place. It underlies much of the Trans-Hudson origin in Saskatchewan, Manitoba. And it is underlain, and it has diamondiferous kimberlite, so it's underlain by very thick, cold lithosphere. So essentially what happened is that the Superior Craton collided and stopped colliding when the Sask lithosphere hit the Superior lithosphere. Both of them are very buoyant, so that's when collision stops. And when collision stops here, it has to pick up somewhere else if collision continues. So here's a map of North America here, the geology, that shows the early accretion of the Churchill Plate, as we've seen earlier in this talk. And then at about 1.83, 1.80, you get Superior collision. And that when that jams and you start to get interference of thick lithosphere with thick lithosphere, it stops, and then all action starts on the southeastern side. And this is what we see with the Central Plains, Mazatzal, Labrador, Aurochlines, and so on, from 1.80 to 1.2. And at 1.2, Amazonia came and hit, and that produced the Grenville origin in yellow. So I don't know how long I've been talking. Maybe not that long. Huh? It's oh yeah, about 45 minutes. Okay, perfect. So perfect time for concluding remarks. There was a lot of material on this in this presentation, but anyway, there's the first one here is that modern light mechanical, thermal, and compositional parameters of the Earth's crust and mantle had been achieved by the Paleoproterozoic, leading to tectonic processes similar to those observed today. Okay? Another thing is accretion, both tectonic and magmatic accretion, played a significant role in the growth of Laurentia and transition. So this is similar to mechanisms that you would see in origins today. Now, the other thing is that indenture tectonics and lateral extrusion influence the style of deformation and the degree of exhumation in a manner similar to modern origin. And I would say that the superior craton, which was the major player here, is particularly indented. It has a very irregular boundary, and that had a strong influence in production of Aurochlines and so on. And last little thought here is the absence of extensional low-angle faults. I don't think there's any yet identified in the transition origin. Is odd because you see that it's very common in modern origin, but it can be perhaps explained in the context of large hot origin. So what I mean here is prior to collision with the superior craton, the Churchill province was a broad area of collision and magmatic accretion. So it was a hot and not particularly thick origin. And when you have hot, weak crust, it doesn't build to a very thick origin. So it's limited in height. So it would tend to ooze out rather than build up and then detach. So maybe that's one way to explain it. So I'm going to stop it there, and thank you for listening, and I will answer your question if people have questions. Thank you.